Time seems to govern everything. Stars are born, atoms change, and every moment appears to move steadily forward. Yet, at the quantum level, the equations of physics suggest something deeply unsettling. Time may not be fundamental at all. It may emerge only when matter, energy, and observation interact. In this documentary, the journey moves beyond clocks and into the deepest structure of reality. If this kind of calm scientific exploration inspires curiosity, please like the video and subscribe to the channel. Now the journey into the mystery of time begins. Across the vast observable universe, time first appears through change, recorded in light. Galaxies shine at immense distances, stars pass through long stages of formation and decline, and clouds of gas carry traces of events that occur far beyond any human lifetime. None of these distant objects is seen in an immediate cosmic present. Light travels at a finite speed, so every image arrives after a journey. The moon appears as it was a little more than 1 second earlier. The sun appears as it was about 8 minutes earlier. Nearby stars are seen years in their past, while remote galaxies are seen millions or billions of years before the present era. The night sky, therefore, holds many ages at once. The expansion of the universe stretches the travelling light, and gravity alters the paths by which some rays arrive. Astronomers combine these effects with carefully tested models to place distant scenes within a coherent sequence of cosmic development. This sequence is called cosmic time. In the standard cosmological model, it is not a clock located outside the universe. It is a useful measure defined for observers who move with the average expansion of matter across very large scales. Within that description, the universe becomes older as space expands, and its average density falls. The most distant light accessible through ordinary telescopes comes from galaxies whose radiation begins its journey when the universe is young. Their light is shifted toward longer wavelengths as space expands. This cosmological redshift gives a measure of how much the universe grows while the light is traveling. A larger redshift usually corresponds to an earlier stage of cosmic history, but the conversion from redshift to age depends on the expansion history. Astronomers reconstruct that history by comparing several independent forms of evidence. Certain exploding stars provide known patterns of brightness and allow distances to be estimated. Large arrangements of galaxies preserve a characteristic scale left by pressure waves in the early universe. Together, these observations indicate that cosmic expansion changes over time rather than proceeding at one constant rate. The evidence also indicates that the recent expansion is accelerating. Dark energy is the name given to the component used in the standard model to describe this acceleration, but its physical nature remains uncertain. Farther back in the visible record lies the cosmic microwave background, a field of faint radiation arriving from every direction. This light begins traveling when the universe is about 380,000 years old. Before that stage, ordinary matter forms a hot plasma in which free electrons repeatedly scatter light. As expansion continues, the plasma cools enough for electrons and atomic nuclei to form neutral atoms. Light then moves freely across space, carrying an image of small variations in density and temperature. Satellites and ground-based observatories map these variations with great precision. Their patterns reveal the geometry, composition, and early expansion of the observable universe. When these measurements are combined with other astronomical data, the Standard Model gives a present cosmic age of about 13.8 billion years. Small differences remain among some methods used to measure the current expansion rate, and researchers continue to examine whether those differences arise from measurement effects, incomplete modeling, or physics beyond the simplest model. Cosmic history also appears in the lives of stars. A star changes because gravity compresses its matter while nuclear reactions transform elements in its interior. Its mass strongly influences the pace. Massive stars consume their central fuel quickly and survive for comparatively short periods. Smaller stars use their fuel slowly and can remain stable for far longer. Astronomers compare a star's brightness, color, chemical composition, and pulsations with models of stellar structure to estimate its age. Star clusters are especially useful because their members generally form at nearly the same time. The pattern of stars leaving their long, stable phase acts as a marker for the age of the cluster. The oldest measured stars and clusters provide a lower limit for the age of the universe. Their estimated ages remain consistent within uncertainties with the age inferred from cosmic expansion and the microwave background. Elements provide another slow record. Some atomic nuclei are unstable and transform into other nuclei at statistically predictable rates. In ancient stars, meteorites, and primitive material from the solar system, the relative amounts of parent and daughter nuclei preserve information about elapsed duration. This method does not date the universe directly, but it places firm ages on matter within it. Meteorites indicate that the solar system forms about 4.57 billion years ago. Chemical abundance, therefore, serves as a kind of observable cosmic memory. Hydrogen and helium dominate the oldest material, while heavier elements accumulate through stellar fusion, stellar explosions, and collisions involving dense stellar remnants. At still larger scales, the changing population of galaxies marks the passage of cosmic eras. Very distant galaxies tend to be smaller, less settled, and more actively forming stars than many nearby galaxies. Their shapes and chemical contents change as they gather gas, create stars merge with neighbors and lose material through energetic processes. Supermassive black holes grow in galactic centers and influence surrounding gas, while the cosmic rate of star formation reaches a broad maximum billions of years ago and then declines. These patterns do not form a perfect universal clock because individual galaxies develop along different paths. They nevertheless supply a statistical chronology when enormous populations are examined together. The immense large-scale universe thus contains many natural records rather than one visible ticking mechanism. Traveling light orders distant events by look-back time. Expanding space stretches wavelengths. Ancient radiation preserves conditions from a young cosmos. Stars record duration in their interiors. Unstable nuclei record it through decay, and galaxies record it through collective change. Each method has assumptions and uncertainties, yet their broad agreement gives confidence that the observable universe possesses a measurable history. Cosmic time in this setting functions as an organizing coordinate tied to an expanding, nearly uniform universe. It allows events across immense distances to be placed within a common model, from the release of ancient radiation to the growth of galaxies and the formation of planets. The result is a calm and consistent outer view of time built from light, matter and change across the widest region that observation can reach. Across the broad universe, cosmic time offers a useful way to arrange the development of matter on the largest scales, yet this shared measure does not describe time as an absolute background. At the level of moving observers and passing light, the idea of one universal present no longer survives. Special relativity describes this region of physics where gravity can be neglected and motion is compared between observers traveling at constant velocity. An inertial observer is one who moves without acceleration in such a setting. Each inertial observer may construct a coordinate system using clocks and measuring rods, and each may regard that system as being at rest. No inertial system holds a privileged status. The laws of physics take the same form in all of them, and the measured speed of light remains precisely the same for observers regardless of the motion of the source or receiver. Every inertial observer measures the same vacuum speed for a light pulse. Space and time must therefore adjust together when observations made in different states of motion are compared. The mathematical rules that connect those observations are called Lorentz transformations. They mix spatial and temporal coordinates while preserving the measured speed of light and the causal structure of events. An event is an occurrence assigned both a place and a time. A flash from a distant star, the collision of two particles, and the meeting of two spacecraft are all events. Different observers can agree that an event occurs even when they assign it different spatial coordinates and different clock readings. Two events judged simultaneous in one moving system need not be simultaneous in another. This relativity of simultaneity is not caused by faulty clocks or delays that could simply be corrected. It remains after the known travel time of light is included. It belongs to the structure of space-time itself. Several clocks rest along a straight line and are synchronized by light signals according to an observer moving with them. Another observer passes the line at constant velocity. Because both observers must measure light at the same speed, the passing observer does not judge the separated clocks to share the same synchronization. Events occurring at opposite ends of the line can carry equal clock readings in one system and unequal readings in the other. Neither result is physically defective. Each follows consistently from the observer's motion and from the invariant behavior of light. The absence of absolute simultaneity removes the universal now imagined in older classical physics. There is no single cosmic sheet containing every event that presently occurs everywhere. Each inertial frame divides space-time into spaces and times in its own way. The relations are exact, measurable, and connected by precise transformations. Once the motion between observers is known, each set of coordinates can be translated into the other. What disappears is not order or physical law, but the assumption that all valid clocks throughout space can be placed into one uniquely correct global pattern. Moving clocks also accumulate different durations. When one clock travels relative to an inertial frame and is later compared with clocks at rest in that frame, its interval between selected events can be shorter. This effect is called time dilation. It applies to every physical process in the moving system, including mechanical motion, atomic transitions, biological aging, and the decay of unstable particles. The moving clock does not feel slowed within its own surroundings. Local processes proceed normally and a nearby clock remains consistent with them. The difference becomes apparent only when separated paths or coordinate systems are compared. Time dilation grows as relative speed approaches the speed of light. Muons are unstable particles that decay rapidly when measured at rest. Many muons produced high in Earth's atmosphere reach the surface because their motion relative to Earth gives them a longer measured lifetime in the terrestrial frame. In the muon's own description, the atmosphere is shortened along the direction of motion, so the surface is reached during the ordinary lifetime. These two accounts describe the same events and produce the same measurable result. Relativity preserves a firm distinction between events that can influence one another and events that cannot. Light emitted from an event spreads outward and defines a light cone, the boundary traced by signals moving at light speed. Events inside the future part of this cone can receive a slower-than-light influence from the original event. Events inside the past part can influence it. For such causally connected events, all inertial observers agree on their order, even though they may disagree about the duration between them. A cause does not become an effect merely because the observer changes motion. Events outside one another's light cones have no possible causal connection under special relativity. They are described as space-like, separated. Different observers may disagree about which of these events occurs first, and some may judge them simultaneous. This freedom produces no contradiction because no signal or influence can pass between them quickly enough to establish a causal sequence. Relativity, therefore, removes universal simultaneity while retaining a stable network of possible causes and effects. The geometry that contains this network is space-time. Space and time are not interchangeable in every respect, but they participate in one unified structure. Different observers trace different routes through it, and their clocks divide those routes according to their own motion. A duration is therefore not merely assigned by distant convention. It is connected to the path taken between events. Even in a region without significant gravity, two clocks can separate, move differently, and later reunite with different elapsed readings. Their disagreement is not an imperfection, it records the geometry of their histories. Special relativity is supported by a wide range of experiments involving precision clocks, rapidly moving particles, electromagnetic signals, and high-energy collisions. No reliable observation reveals an absolute frame of rest or a universal system of simultaneity. The theory does not claim that time is unreal, nor does it erase measurable duration. It shows instead that time is not a single river flowing identically for every observer across all of space. Each clock measures along its own motion while the laws connecting different measurements remain stable. At this level, nature retains temporal order where causal influence is possible, yet it offers no unique present shared by the entire universe. Beyond the nearly gravity-free setting of special relativity, space-time is no longer a fixed stage. Stars, planets, gas radiation, and every other form of energy participate in shaping its geometry. General relativity describes this deeper structure by treating gravity not as an invisible force pulling across space, but as the behavior of matter and light within curved space-time. It determines the paths that freely moving objects follow, and those paths are observed in planetary systems, galaxies, clusters, and the propagation of light across the universe. Within a small sealed laboratory, the effects of a uniform gravitational field can resemble the effects of steady acceleration. A person standing on a planet feels support from the ground, while a freely falling person feels locally weightless even though gravity remains present. Weightlessness, therefore, reflects the absence of supporting pressure, not the absence of gravity. This local connection between gravity and acceleration changes the role of geometry. On a flat sheet, parallel lines remain parallel, and familiar rules relate distances and angles. On a curved surface, paths that begin parallel may converge or separate. The surface of a sphere provides a simple spatial comparison, since routes that appear parallel near the equator can meet near a pole. Space-time curvature is more complete than this image because it includes the temporal dimension as well as the three spatial dimensions. It also does not require the universe to bend into some higher external space. Curvature can be measured entirely from relationships within space-time through the behavior of clocks, light rays, and freely falling bodies. A freely moving body follows a geodesic, meaning the straightest available path, through a curved geometry. Near the Sun, a planet follows such a path and produces what appears spatially as an orbit. The planet is not continually pulled away from a straight route through an independent arena of space and time. Its root is already straight in the fuller geometry of space-time, even though its projection into ordinary space curves around the Sun. Light follows geodesics as well. When starlight passes near a massive body, its path bends. Observations of this deflection provide a direct test of the geometric description of gravity. The amount and form of curvature depend on more than mass alone. Energy, momentum, pressure, and stress all contribute. A quiet star, a beam of radiation, a rapidly moving particle, and a region filled with pressure influence space-time in ways described by the same general framework. The central relation of general relativity connects the distribution of these physical contents with the curvature around them. The relation works in both directions as one couple system. Matter and energy shape the geometry, while the geometry guides the motion and evolution of matter and energy. Unlike the fixed geometry used in special relativity, this geometry can change. Moving masses can create disturbances that travel outward as gravitational waves. These waves are ripples in space-time curvature, not vibrations moving through an ordinary material. Binary systems containing black holes or neutron stars lose orbital energy as the waves carry energy away. Detectors on Earth observe tiny changes in the relative separation of suspended mirrors as a wave passes. The measured signals agree closely with predictions of general relativity and reveal motions in regions that emit little or no ordinary light. A massive galaxy or cluster can act as a gravitational lens, bending light from objects behind it. A single background galaxy may appear stretched into arcs or repeated in several images. The exact pattern depends on the distribution of visible and unseen matter along the path. Astronomers use these distortions to map mass, including dark matter, that emits no detectable light. The lens does not behave like a piece of glass with a material surface. Near a compact mass, the curvature can become strong. A black hole forms when matter is compressed within a region from which no future directed path can carry a signal to distant space. The event horizon is the boundary separating events that can still communicate outward from those that cannot. It is not a solid shell, and a sufficiently large black hole may produce no sharp local marker at the horizon for a freely falling observer. Far from the hole, the geometry determines the motion of orbiting material and the path of radiation. Close to it, stable circular motion becomes impossible below a certain region, and matter can plunge inward while heating and radiating before crossing the horizon. General relativity also describes the universe as a whole, a nearly uniform distribution of matter, and radiation allows space-time itself to expand. Galaxies that follow this large-scale flow become more widely separated without moving through a pre-existing emptiness in the ordinary sense. The scale of spatial distances changes as the cosmic geometry evolves. The equations permit many possible cosmic histories, and observations select the models that best match the measured expansion, ancient radiation, and growth of structure. Within the accepted model, ordinary matter, dark matter radiation, and dark energy contribute differently to the changing geometry. Although curvature is global, every measurement begins locally. A small, freely falling laboratory can behave almost as though gravity is absent. Over a larger region, however nearby, falling paths may approach or separate. These differences are tidal effects, and they reveal curvature directly. Ocean tides provide a familiar, weak example because different parts of Earth experience slightly different gravitational motion. Near a compact star or black hole, tidal differences can become much stronger. No change of coordinates can remove them from an extended region because they represent a physical property of space-time rather than a choice of description. The geometry of general relativity is therefore active rather than passive. It carries waves, responds to energy guides, motion, and evolves with the contents of the universe. Coordinates remain useful labels, but they are not themselves physical objects, and different coordinate systems can describe the same space-time. Observable statements depend on relationships that survive a change of labels, such as whether paths meet, whether light reaches a detector, or how freely falling bodies move relative to one another. Time belongs to this geometry and cannot be separated into a universal background unaffected by matter. At this scale, it remains part of a continuous space-time, whose shape is tested through orbits, light waves, tides, and the expansion of the cosmos. Within curved space-time, time becomes most concrete where a clock follows a particular path. The line representing that history is called a world line. It passes through every event occupied by the clock from one local moment to the next. The duration accumulated along a world line is proper time, meaning the time directly registered by a suitable clock traveling on that path. Proper time does not belong to a distant coordinate grid or to an observer watching from elsewhere. It belongs to the sequence of nearby events through which the clock itself moves. An ideal clock measures this duration without allowing its construction to introduce significant error. It can be imagined as a regular pulse, a stable oscillation, or any repeatable physical process whose cycles can be counted. Pendulums, rotating wheels, vibrating crystals, and transitions within atoms rely on different mechanisms. Yet relativity predicts that well-controlled clocks following the same path accumulate the same elapsed time. A clock never measures time at a remote event directly. Signals must travel from the remote location, and their arrival includes information about both the source and the journey. To construct a wider coordinate system, observers place clocks throughout space or exchange light signals according to an agreed procedure. Coordinate time is the numerical label assigned to events within that system. It is extremely useful for describing motion across an extended region, but it need not equal the proper time recorded by every clock inside the region. Different coordinate choices may assign different time labels to the same events while leaving local clock readings and physical coincidences unchanged. The distinction becomes clear when two clocks begin together separate and later meet again. At the first meeting, both readings can be set to the same value. At the second meeting, their readings can be compared at one location without correcting for signal delay. If their paths through spacetime differ, their elapsed proper times may also differ. The comparison is direct and permanent. Each records the duration of its own route between the shared events. In flat space-time, relative motion is enough to create such a difference. A clock that remains in one inertial state between the meetings follows a different path from a clock that travels away, changes motion, and returns. The returning clock generally accumulates less proper time. This arrangement is often described through traveling twins, but the result concerns paths and clocks rather than human perception. Acceleration allows the traveling path to turn back toward the reunion, yet acceleration alone is not a simple substance that slows a clock. The complete geometry of the two world lines determines the final difference. A light clock offers a quiet model of this geometry. Two mirrors face one another, and a pulse of light moves repeatedly between them. In the frame where the mirrors rest, the pulse travels straight across the gap and back. In a frame where the clock moves sideways, the same pulse traces a longer diagonal route between reflections. Because every inertial frame measures the same speed of light, the moving cycle occupies a longer interval of coordinate time. The clock's own local cycle remains normal. The comparison reveals how differing paths through space and time preserve the shared behavior of light while producing different accumulated durations. Proper time applies only along paths that physical objects moving slower than light can follow. Such paths are called time-like because their events can be connected by a material clock. Light follows a different limiting kind of path. Along a light ray, the space-time interval has a special value that does not function as the ticking time of a traveling clock. A photon, therefore, has no valid rest frame in relativity. Statements that describe what a photon experiences treat the theory too loosely, because no ordinary clock can move beside light and remain at rest relative to it. For a material clock, every sufficiently short part of its world line has a local rest frame. Within that small region, the clock is at rest at the chosen event, and ordinary nearby processes can be described without referring to its motion through a larger coordinate system. Linking these local frames along the route allows proper time to accumulate continuously, even when the clock accelerates or travels through curved space-time. The construction remains local at each step. It does not require a single frame that accompanies the clock across its entire journey. The clock hypothesis states that an ideal clock's instantaneous rate depends on its instantaneous motion, not directly on its acceleration. Acceleration can still influence a real clock by deforming its parts, changing its temperature, or disturbing its mechanism. Those practical effects must be separated from relativistic path dependence. Experiments with unstable particles and precision clocks support the ideal description across broad ranges of motion. When engineering disturbances are controlled, clocks behave according to the space-time intervals along their trajectories. This behavior gives proper time an operational meaning. An operational quantity is one connected to a defined measurement procedure. A physical clock is carried along a path, its cycles are counted, and its reading is compared with another clock when the two occupy the same event. No assumption about a universal present is required. The result depends on the route between meetings and can be predicted from the space-time geometry. Local measurements also protect the consistency of physics. A heartbeat, a chemical reaction, a mechanical oscillator, and an atomic process all unfold together in the same local time when they share a path and environment. No traveler detects personal slowing by inspecting nearby processes. Differences emerge when histories are brought into comparison. This is why relativistic time is neither an illusion nor a variable flow sensed within a single laboratory. It is a measurable relation among world lines. Proper time, therefore, narrows the meaning of duration from a universal background to a property of a physical history. Coordinates can cover broad regions and organize distant events, but a clock carries only the time along its own route. When paths separate, each accumulates duration locally. When paths meet, their records can reveal different totals. The comparison remains objective because all observers present at the reunion can examine the same readings. Within relativity, the most immediate time is not spread everywhere at once. It is traced quietly along each possible journey through space-time. Around planets, stars, and other massive bodies, clocks at different locations do not accumulate time at identical rates. General relativity describes this difference as gravitational time dilation. A clock deeper within a gravitational field records less elapsed time than a comparable clock farther from the source, provided their motion and other influences are properly accounted for. The clock does not malfunction, and its local rhythm appears normal beside nearby processes. The difference becomes visible when signals or reunited clocks allow their records to be compared. When radiation travels upward from a lower region of a gravitational field, a receiver higher above measures a lower frequency. This change is called gravitational redshift. Here, the emitting and receiving apparatus occupy regions where proper time accumulates at different rates. A fixed number of wave cycles is distributed across different intervals, measured by the two clocks. Atomic clocks placed at different heights acquire measurable differences because the higher clock lies slightly farther from Earth's center. Even a vertical separation comparable to the height of a room can produce a detectable shift with the most precise clocks. Earlier experiments measure the frequency change of radiation moving through a tower, while later comparisons use aircraft rockets, satellites, and laboratory clocks. The results agree with general relativity within increasingly narrow uncertainties. Motion also alters accumulated time, as special relativity describes. A clock carried by a satellite moves rapidly and occupies a weaker part of Earth's gravitational field than a clock on the surface. The effects of speed and gravity act in opposite directions for many satellite orbits. Engineers calculate both when designing navigation systems. Without relativistic corrections, the timing errors would grow and produce substantial mistakes in positions determined from radio signals. Relativistic time is therefore present in ordinary global infrastructure, even though its local changes remain far below direct human sensation. Near a dense star, gravitational time dilation becomes stronger. Radiation leaving the stellar surface reaches distant space with a lower measured frequency. The amount of redshift carries information about the relation between the star's mass and radius. For white dwarfs and neutron stars, this measurement can help test models of compact matter, although motion, atmosphere, magnetic fields, and observational uncertainties must also be considered. The distant and local measurements simply refer to different space-time paths and different standards of duration. Near a black hole, comparisons become more extreme. In coordinates tied to a distant stationary observer, signals emitted from matter approaching the event horizon arrive redshifted and delayed. Their energy fades below practical detection, so the infalling matter appears to slow and dim. A clock falling with the matter crosses the horizon after a finite amount of its own proper time. Assuming the black hole is sufficiently large and tidal forces remain survivable at that location. These descriptions are consistent because they use different ways of assigning times to distant events. The horizon marks a causal boundary in spacetime. Outside it, a stationary clock must resist inward free fall, and the required acceleration grows without bound as the horizon is approached in the idealized description. A freely falling clock follows a different path and remains locally regular as it crosses. The contrast shows why statements about time stopping require careful reference to the chosen observer and coordinates. Gravitational time dilation reveals that matter influences duration through geometry. Height motion and path determine how much proper time a clock gathers. Clocks placed in different gravitational environments can separate by tiny fractions of a second or by far greater amounts near compact objects. Each clock remains locally ordinary while comparison exposes the difference written into space-time itself. In the visible world of warm objects, flowing gases, breaking materials, and living systems, time carries a clear direction. A cup cools after it is placed in a room, ice melts in warmer water, and scattered fragments do not naturally gather into an intact vessel. The direction they establish is called the thermodynamic arrow of time. The arrow is described through entropy, a quantity related to how many microscopic arrangements are compatible with the large-scale condition of a system. A large-scale condition is called a macro state. Temperature, pressure, volume, and density help define it without specifying the position and motion of every particle. Beneath one macro state lie many microstates, which are the detailed arrangements of all the particles. A state with higher entropy generally corresponds to a much larger number of possible microscopic arrangements. Consider gas confined to one side of a container. When a barrier is removed, the gas spreads throughout the available volume. There are overwhelmingly more arrangements in which molecules occupy both sides than arrangements in which every molecule remains crowded into one side. The second law of thermodynamics states that the entropy of an isolated macroscopic system tends not to decrease. This is a statistical law rather than a ban on every possible fluctuation. A small collection of particles can briefly move toward a less probable arrangement. In a system containing an enormous number of particles, however, a large spontaneous decrease becomes extraordinarily unlikely. Ordinary objects, therefore, show a stable direction from less probable macroscopic conditions toward more probable ones. When a warm body touches a cooler body energy spreads until their temperatures approach equilibrium. Equilibrium is the condition in which no large net flow remains, and the accessible energy is distributed among many microscopic possibilities. The reverse concentration of dispersed energy into the originally warmer body is not forbidden by energy conservation alone. It is simply so improbable for a macroscopic system that it is not observed in ordinary circumstances. Entropy does not mean disorder in every simple visual sense. A carefully stacked deck and a shuffled deck can illustrate probability, but physical entropy depends on defined macroscopic variables and available states. Crystals may appear highly ordered while forming naturally under conditions that release heat into their surroundings. The entropy of the crystal can decrease while the total entropy of the crystal and environment increases. The second law concerns the complete isolated system, not every selected part considered alone. Earth continually receives concentrated energy from sunlight and releases more diffuse infrared radiation into space. Weather systems, organisms, and machines can maintain internal organization by increasing entropy elsewhere. A living cell does not violate thermodynamics when it builds complex molecules. It consumes usable energy, releases heat and waste, and participates in a larger process whose total entropy rises. Memory also rests within this direction. A physical record forms through a change in matter, whether it appears as altered molecules, magnetic alignment, ink, or neural activity. Creating and preserving records requires physical processes that dissipate energy. Records therefore accumulate within a world where traces of lower entropy conditions remain in higher entropy surroundings. The past leaves fossils, photographs, scars, and stored signals, while comparable records of the future do not already exist. The thermodynamic arrow does not by itself prove that time is a substance flowing forward. It identifies an asymmetry in the behavior of large systems. Clocks can count intervals in either direction on paper, but physical processes establish records aging, cooling, and decay along the direction in which entropy generally increases. This macroscopic arrow is steady because vast numbers of particles make departures from it overwhelmingly rare. Beneath the stable direction seen in cooling, mixing, and decay, many microscopic laws possess a different temporal character. The equations governing particles and fields often allow a valid sequence of events to be transformed into another valid sequence running in the opposite temporal direction. This property is called time reversal symmetry. It does not mean that time physically reverses inside matter. It means that the fundamental description may permit motions whose velocities and related quantities are reversed without violating the law that governs them. A simple collision illustrates the idea. Two particles approach, interact, and separate along new paths. If every motion is reversed precisely, the outgoing particles return, collide, and retrace the original incoming paths. Classical mechanics generally allows both histories. Electromagnetic interactions also possess closely related reversible behavior when all relevant quantities are transformed correctly. The equations do not select one history as naturally forward and the other as naturally backward. Quantum mechanics shares much of this symmetry. A quantum state evolves according to a rule that preserves information about its possible development. For many isolated systems, the mathematical evolution can be reversed. If the complete final state is known with perfect accuracy and the appropriate reversed evolution is applied, the earlier state can in principle be recovered. Ordinary spreading and mixing do not arise because the microscopic rule continually destroys the past. Yet real macroscopic systems contain immense numbers of particles. Their exact states cannot be controlled, and tiny correlations spread into surrounding matter, radiation, and motion. Reversing a shattered object would require reversing every fragment, vibration, air molecule, emitted photon, and thermal disturbance with extraordinary precision. Any neglected detail prevents the original arrangement from returning. The reverse history remains compatible with many microscopic laws, but its initial condition is overwhelmingly special. This distinction connects microscopic reversibility with increasing entropy. A low entropy macro state occupies a small portion of the available microscopic possibilities. As the system evolves, it moves into conditions represented by far more possible arrangements. Nearly every accessible route leads toward equilibrium, while only an extremely narrow collection produces a coordinated return. The microscopic equations permit that return, but probability makes it absent from ordinary experience. Not every fundamental interaction is perfectly unchanged under a simple reversal of time. Experiments involving certain unstable particles reveal small violations connected with the weak nuclear interaction. These effects are related to asymmetries between matter and antimatter under combined transformations. They demonstrate that time reversal symmetry is not exact throughout all known particle physics. However, these subtle violations do not explain the familiar thermodynamic arrows seen when heat spreads or objects break. Their scale and character differ from the statistical irreversibility of macroscopic matter. Quantum measurement also appears to introduce direction because a range of possible outcomes becomes one recorded result. In practical descriptions, this change seems unlike ordinary reversible evolution. Environmental interaction rapidly distributes information about alternatives through surrounding particles, a process called decoherence. Decoherence explains why interference between macroscopic alternatives becomes effectively inaccessible, although interpretations differ over what the resulting quantum state means. It does not provide a universally accepted independent law that makes time fundamentally flow. At the microscopic level, nature, therefore, offers no broad mechanism resembling the everyday march from intact objects toward fragments. Most basic evolution remains reversible or nearly reversible, while observed irreversibility emerges from boundary conditions, probability, environmental interaction, and the enormous number of hidden details. The direction of ordinary time rests less in a universal preference within each particle than in the special conditions from which large systems begin and the overwhelmingly probable ways their many components spread. Within atoms, time is measured through changes that occur with remarkable regularity. An atom contains a compact nucleus surrounded by electrons described by quantum states. These states do not permit every possible energy. Instead, they form discrete energy levels. When an atom changes from one allowed level to another, it can absorb or emit electromagnetic radiation with a characteristic frequency. Frequency describes the number of wave cycles occurring during a chosen interval. Because atoms of the same isotope share the same internal structure, under controlled conditions their transitions provide stable references for clocks. An atomic clock does not simply count particles changing state, it uses an electromagnetic oscillator, often producing microwave or optical radiation, and carefully adjusts that oscillator until its frequency matches a selected atomic transition. A detector measures how strongly the atoms respond. A feedback system then corrects the oscillator whenever it drifts away from resonance. Once the frequency is stabilized, the clock counts the oscillator's cycles. Duration emerges operationally from this repeated quantum process. The international definition of the second is based on a transition in atoms of cesium-133. 1 second corresponds to 9,192,631,770 cycles of radiation associated with a specified transition under defined conditions. Writing the number in full does not imply that individual atoms contain tiny mechanical pendulums. The transition supplies a reproducible frequency, while the complete clock includes lasers, microwave systems detectors, shielding temperature control, and electronic counting equipment. Several physical effects can disturb the reference. Motion changes measured frequency through the Doppler effect. Magnetic and electric fields shift atomic energy levels, Collisions between atoms can alter their response, and thermal radiation from surrounding surfaces can produce small changes. Atomic motion also broadens the observed transition. Modern clocks reduce these influences by cooling atoms, trapping them, isolating selected transitions, and comparing measurements under carefully controlled conditions. Optical clocks use transitions with much higher frequencies than cesium microwave clocks. Their faster oscillations divide a second into finer cycles, allowing exceptionally precise comparisons. Ions can be confined by electromagnetic fields, while neutral atoms can be held in an optical lattice formed by laser light. Specialized laser systems probe narrow transitions, and frequency combs connect optical oscillations with countable electronic signals. These clocks have reached such sensitivity that small differences in height within Earth's gravity can produce measurable differences in accumulated time. Atomic clocks support satellite navigation, communication networks, astronomy geodesy, and tests of fundamental physics. Clocks based on different atomic species can be compared over long periods to search for any variation in quantities regarded as constants of nature. No confirmed change has appeared at established sensitivity. Their agreement also tests relativity, because transported clocks and clocks at different heights accumulate the predicted differences. Despite their precision, atomic clocks do not reveal a universal quantum substance called time. They compare one regular physical process with other changes. Their operation assumes the temporal framework used by quantum mechanics and relativity, while their readings provide measurable intervals within that framework. Each clock remains a physical system influenced by motion, gravity fields, temperature, and quantum uncertainty. Atomic transitions, therefore, form a quiet bridge between abstract duration and matter. Through stable energy differences and counted cycles, the passage assigned to events becomes a reproducible record carried by atoms themselves. In standard quantum mechanics, time enters the description differently. From position, momentum, and other measurable properties, a particle can occupy a quantum state in which its position is not sharply defined. Position is represented by an observable, a mathematical quantity connected to possible measurement outcomes. Momentum, angular momentum, and energy are also represented by observables. Time usually receives no matching operator in the basic formulation. It appears instead as an external parameter that labels how the quantum state changes. A quantum state contains the information needed to calculate probabilities for possible measurement results. As the time parameter advances, the state evolves according to the Schrödinger equation. The equation connects the rate of change of the state with its energy. Time acts like a coordinate supplied from outside the quantum system, comparable to the reading of an ideal laboratory clock that is not itself included in the calculation. This arrangement works with extraordinary accuracy for atoms, molecules, solids, and subatomic particles. The distinction has practical meaning. A measurement of position can return one of many possible locations. A measurement of energy can return one of the allowed energy values. time is usually not measured in this same manner. An experiment records when an event occurs by consulting a separate physical clock. The clock provides a temporal label while the quantum system supplies another outcome. In this standard, treatment time organizes measurements rather than appearing as one more property measured within the system. Difficulties arise when an experiment seeks a time associated with a quantum event. A researcher may consider the arrival time of a particle, the duration of tunneling, or the moment of a decay. No single universal time operator describes all such situations. Instead, each problem requires a measurement model suited to the physical arrangement. A detector clock and interaction must be specified. Different definitions can describe different operational aspects of duration, and care is needed when comparing them. This unusual role does not show that time is absent from quantum physics. Quantum interference depends sensitively on temporal evolution. Atoms absorb radiation at frequencies determined by energy differences. Unstable states develop characteristic decay probabilities over time. Lasers, transistors, and magnetic resonance rely on quantum changes whose timing is accurately predicted. The theory clearly describes temporal behavior, but it generally does so against a background clock. The background is treated classically. It has a definite reading and does not enter a superposition of different times. This approximation is reasonable when a laboratory clock is much larger than the quantum system, and its uncertainties are negligible for the experiment. Every real clock is made of quantum matter, yet its detailed quantum state can often be ignored, just as the motion of a heavy laboratory table can be ignored while a small particle is studied. The separation becomes less secure when the clock must be included within the quantum system. Its reading can then possess uncertainty, become correlated with other states, and be disturbed by interaction. The simple external parameter remains useful, but it no longer gives a complete physical account of how one subsystem records change in another. Standard quantum mechanics, therefore, contains time without treating it like an ordinary quantum observable. It assumes a stable temporal background, uses that background to describe evolving states, and connects predictions to clocks outside the chosen system. This structure is experimentally successful, yet it leaves a conceptual boundary between quantum matter and the time used to describe it. Within quantum theory, energy governs how a state changes as the external time parameter advances. This role is expressed through the Hamiltonian, the mathematical operator representing the total energy of a system. It includes contributions from motion, interactions, external fields, and other physical conditions. Once the Hamiltonian and an initial quantum state are specified, the Schrödinger equation determines the state's later evolution. Energy, therefore, acts as the generator of temporal change. A state with one precisely defined energy develops in a particularly simple way. Its overall phase changes steadily with time, while the probabilities of measurements that do not depend on that phase can remain constant. Such a state is called stationary, even though the underlying quantum description continues evolving. Stationary does not mean that every internal feature resembles a classical object frozen in place. It means that observable probability distributions remain unchanged under the specified conditions. More visible change appears when a state contains a superposition of different energy values. Each energy component accumulates phase at a different rate. Their relative phases then shift, altering interference patterns and other measurable quantities. Oscillations in atoms, molecules, neutrinos, and many laboratory systems arise through this relation. The pace of quantum evolution is tied to differences in energy rather than to an independent internal clock hidden inside each particle. Energy and time are sometimes linked through an uncertainty relation. But this relation differs from the uncertainty between position and momentum. Position and momentum are both represented by operators, and their measurement uncertainties follow from the structure of quantum states. In standard quantum mechanics, time is usually a parameter rather than an operator. A time and energy uncertainty relation can instead describe several related limits, such as the duration required for a state to change significantly, or the connection between the lifetime of an unstable state and the width of its measured energy distribution. A short-lived excited state often produces a broader spectral line than a long-lived state. This broadening reflects the finite duration over which the state remains available to emit radiation. It does not mean that energy conservation can simply be violated for a short interval. Energy remains conserved when the Hamiltonian has no explicit dependence on time and the complete physical system is treated consistently. Informal claims that nature borrows energy briefly confuse a useful estimate with a physical transaction. The speed at which a quantum state can become distinguishably different also has limits connected to its energy distribution. A state with little energy uncertainty may evolve slowly in the space of possible states, while a broader distribution can permit faster change. These quantum speed limits depend on the preparation and dynamics of the system. They constrain computation, control, and measurement, yet they do not establish a smallest universal unit of time. When the Hamiltonian itself changes because an external field is adjusted, energy can pass between the system and the apparatus, producing that field. The time-dependent description then includes the influence of the laboratory. A fuller account can place both system and apparatus within one larger energy-conserving framework. Energy thus provides the structure by which quantum states evolve, while time supplies the parameter ordering that evolution. Their relation is deep but not symmetrical. Energy is measured as a property of a system. Time usually remains the background against which that property generates change. This difference is central to the unresolved question of whether temporal order is fundamental or arises from relations inside a more complete quantum description. When a clock is placed fully inside quantum physics, it ceases to be an ideal background object. It becomes a material system with a state energy position and interactions. Its reading must be encoded in some changing physical quantity, such as the position of a pointer, the phase of an oscillation, or the population of an atomic level. These quantities are subject to quantum uncertainty. A clock can therefore provide a useful temporal reference without possessing a perfectly sharp reading. A clock requires distinguishable states that occur in a regular sequence. Greater resolution demands that these states change rapidly enough to mark shorter intervals. Producing rapid, reliably distinguishable change generally requires suitable energy resources and a broad enough range of energy values. A clock confined to a finite system cannot supply unlimited resolution for unlimited duration. Its mechanism eventually repeats, drifts, interacts with its surroundings, or accumulates uncertainty. The reading process also matters. Extracting time information requires an interaction between the clock and another system or detector. That interaction can disturb the clock. If the measurement is weak, it may preserve the clock more gently while providing less information. If it is strong, it may identify the reading more clearly while altering later evolution. The exact balance depends on the clock design and the physical quantity being measured. There is no single universal limit that applies in the same form to every clock. Quantum clocks also carry finite mass and occupy finite regions of space. A highly localized clock has uncertainty in momentum which causes its position to spread during motion. Increasing its mass can reduce some effects, yet mass also produces gravity. At ordinary laboratory scales, the gravitational influence is negligible. In attempts to imagine clocks with extreme precision and extreme localization, both quantum mechanics and gravity become relevant. Arguments combining these theories suggest fundamental restrictions, but no complete experimentally confirmed theory determines one universal smallest measurable interval. Environmental interaction creates further limitations. Stray electromagnetic fields, collisions, thermal radiation vibrations and gravitational changes can shift the clock's frequency. Decoherence suppresses delicate superpositions and makes the clock behave more classically, but it also carries information into the environment. Engineers isolate clocks from disturbances while maintaining enough interaction to prepare, control, and read them. Precision, therefore, emerges from a carefully managed openness rather than perfect separation. Two quantum clocks prepared identically do not necessarily give perfectly identical readings in every single trial. Their outcomes form statistical distributions. Repeated measurements and comparisons reduce uncertainty in estimated rates, although systematic shifts remain important. Entangled states can improve certain timing measurements beyond limits achievable with independent particles, but loss and noise can weaken that advantage. A clock may also become correlated with the system it measures. Its reading then cannot always be treated as an independent label. Information about the system is connected with information about the clock, and the combined state may need to be described as one whole. Temporal statements become conditional, referring to the state of one part, when the clock part displays a particular reading. Physical clocks, therefore, approximate time rather than revealing a flawless external parameter. Their limits arise from finite energy, quantum uncertainty, measurement, disturbance, environmental coupling, and gravity. These limits do not prove that time disappears. They show that every recorded duration is produced by a physical process, and every such process belongs to the same quantum world whose changes it is used to measure. When every clock is treated as part of the quantum world, time can be described through relations between physical systems. One subsystem is chosen to function as a clock, while another is treated as the system whose change is being tracked. Instead of referring first to an external temporal parameter, the description asks how the system is arranged when the clock occupies a particular state. Temporal order then appears through correlations inside the combined quantum state. A simple clock may contain a quantity that changes regularly, such as a rotating phase or a sequence of distinguishable states. If the clock becomes correlated with another subsystem, one clock reading is associated with one system state, while a different reading is associated with another. The combined state can contain all these correlations. An observer using the clock assigns change to the system by conditioning its description on a selected clock reading. Entanglement can support this structure. Entanglement is a quantum relation in which the joint state of two systems cannot be reduced to separate independent states. Measurements on the parts then display correlations stronger or more complete than a classical mixture would provide. In relational models of time, the clock and the observed system may become entangled so that their states change together in a coordinated pattern. One influential approach is associated with the Page and Wouters mechanism. In an idealized version, the total combined system occupies a stationary state with no evolution relative to an outside time. Within that state, however, correlations between the clock and the remaining subsystem reproduce an effective sequence. Relative to one clock reading the subsystem has one state, relative to another reading it has another. Internal observers who use the clock can therefore recover a form of ordinary quantum evolution even though the complete description appears timeless. This result depends on assumptions. The clock must have states that distinguish readings well enough, and its interaction with the observed system must be controlled. A finite clock has limited resolution and may repeat. A clock strongly disturbed by the system can fail to provide a stable reference. Different choices of clock can also produce different internal descriptions. Researchers study how these descriptions relate and under which conditions they lead to consistent, observable predictions. Laboratory experiments can simulate features of relational time using entangled photon spins or other controlled quantum systems. Such demonstrations test the mathematics of conditional states and correlations. They do not show that the universe as a whole has been proven timeless. The experiments take place within ordinary laboratory time and use external equipment to prepare and measure the systems. Their value lies in showing that apparent evolution can be represented relationally in carefully constructed quantum arrangements. Relational time also resembles a broader principle already present in physics. A position is usually meaningful relative to another object or coordinate system. A velocity is relative to a chosen frame. General relativity makes the geometry of time dependent on physical paths and gravitational conditions. Quantum relational models extend this emphasis by making one changing system the reference for another. The approach does not establish that time is merely an illusion. It offers a way to recover temporal statements without assuming an inaccessible clock outside the complete system. Change remains observable as correlation sequence and conditional probability. What may disappear is the need for a universal external parameter governing everything at once. Within this view, time is carried by relations among quantum systems, and its familiar flow emerges from the ordered records those systems hold about one another. At the boundary between general relativity and quantum theory, the familiar background of time becomes difficult to preserve. General relativity treats space-time geometry as a physical changing entity. Quantum mechanics usually assumes that a state evolves against a fixed temporal parameter supplied from outside the system. When gravity itself must obey quantum principles, the geometry that defines distances, durations, and causal relations can no longer remain a classical stage. This conflict becomes important in regions where matter is compressed to extreme density, or where cosmic geometry approaches conditions beyond the reliable reach of classical relativity. General relativity predicts singular behavior inside idealized black holes and near the earliest boundary obtained by extrapolating standard cosmology backward. These predictions indicate that the classical theory becomes incomplete there. Quantum effects are expected to matter, but no experimentally confirmed theory yet provides a complete description of those regimes. Quantizing a physical system usually begins by identifying its measurable variables and allowing them to possess quantum uncertainty and superposition. Applied to gravity, this procedure suggests that geometry itself may occupy quantum states. A region may not have one perfectly definite curvature or one exact relation between spatial and temporal intervals. Different possible geometries may contribute to the state. The concepts used to place events in a fixed order can then become uncertain. Ordinary quantum field theory successfully describes particles and fields on a predetermined space-time. It combines quantum principles with special relativity and can also operate approximately on certain curved backgrounds. In these calculations, space-time remains classical while matter is quantum. This separation supports predictions concerning particle interactions, radiation around black holes, and fields in an expanding universe. It is powerful, but it does not describe a spacetime that is itself in a quantum superposition. Several research programs attempt to move deeper. Canonical quantum gravity rewrites general relativity in a form resembling the evolution of a dynamical system and then applies quantum rules to the geometry. Loop quantum gravity investigates quantum states built from discrete relational structures associated with areas and volumes. String theory represents fundamental ingredients through extended quantum objects and includes a particle-like excitation with the properties expected of a graviton. Other approaches explore causal structures, discrete histories, emergent geometry, or quantum information. None currently possesses decisive experimental confirmation as the final theory. A central difficulty arises from coordinate freedom. In general relativity, labels assigned to places and times have no independent physical meaning. The same spacetime can be described with many coordinate systems. Physical predictions depend on relationships among events, fields, and observers. When the geometry is quantized, an external clock coordinate cannot be inserted without risking the introduction of a preferred structure, absent from the original theory. Instead, one variable within the universe may be selected as an internal clock. Other variables are then described relative to it. This method can work in limited models, but different clock choices may be useful in different regimes, and no single internal variable must remain regular everywhere. The resulting temporal description can be local and approximate rather than universal. Quantum gravity therefore reaches beneath clocks and beneath the geometry along which clocks travel. Time is no longer simply attached to an unchanging background, because the background belongs to the quantum system. At this depth, the task is not merely to quantize matter within time. It is to explain how measurable duration and causal sequence arise when the structure defining them is itself uncertain. In canonical approaches to quantum gravity, the deepest mathematical description can appear to contain no external time at all. General relativity is first rewritten so that the geometry of space is described on a sequence of spatial slices. Each slice represents a possible arrangement of gravitational and material fields. In classical theory, the slices can be related through spacetime geometry, but the choice of how they are labeled is not unique. The labels function as coordinates rather than observable universal clock readings. When this formulation is quantized, the state becomes a quantum description of possible spatial geometries and matter configurations. A central relation is commonly called the Wheeler-DeWitt equation. Unlike the ordinary Schrödinger equation, it does not contain an external time parameter governing the evolution of the universal state. Instead, it imposes a constraint on which combined configurations are physically allowed. The resulting state of the universe can therefore look frozen. This timeless appearance is known as the problem of time. It arises because ordinary quantum mechanics expects a background time, while general relativity treats temporal coordinates as part of a geometry whose labeling can be changed. The Wheeler-DeWitt framework respects that freedom by avoiding a preferred external clock. Yet observations describe change memory motion and ordered events. A satisfactory interpretation must explain how those familiar features arise from the constrained state. The word frozen can be misleading. The complete mathematical state may lack external evolution while still containing correlations among its variables. One part of the state can serve as an internal clock and other parts can change relative to it. A scale describing the size of a model universe may act as a clock in some circumstances. A matter field may perform that role in others. Conditional probabilities then describe the likelihood of one configuration when the chosen clock variable has a certain value. No internal clock is automatically suitable everywhere. A variable may increase for one period, stop, reverse direction, or become strongly uncertain. Different choices can lead to descriptions that are difficult to compare. These complications show that recovering time is not simply a matter of renaming one coordinate. The chosen clock must behave regularly enough to organize physical change, and predictions should remain consistent when another valid clock is used. Approximations can recover a more familiar structure. If part of the gravitational state behaves almost classically, it can supply an effective space-time background. Matter fields then evolve approximately according to ordinary quantum theory with respect to an emergent time parameter. This semi-classical treatment helps connect the timeless constraint with the world of clocks and laboratory processes. It remains an approximation rather than a complete resolution. The Wheeler-DeWitt equation is not a directly tested final law of nature. Its exact form faces mathematical ambiguities, including choices about how quantities are ordered and how physical states are defined. More complete quantum gravity programs handle these issues differently. Researchers also debate what the universal quantum state represents and how probabilities should be interpreted without an external observer. The timeless constraint therefore provides a precise reason that time may not appear at the most fundamental quantum level. It does not prove that change is unreal or that all events coexist without distinction. It shows that when the entire geometry is included in the quantum system, no outside clock remains available. Temporal experience must then be reconstructed from internal correlations, approximate geometry, and physical records contained within the universe itself. At the deepest boundary presently reached by theory, time may emerge from structures that do not themselves contain a universal clock. This possibility does not mean that measured duration is unreal. Clocks compare physical processes' relativity, predicts their differing rates, and quantum theory accurately describes changing states. Emergence means that these familiar temporal features may arise collectively under particular conditions, much as temperature arises from the motion and distribution of many particles. One route begins with semi-classical geometry. A quantum state of gravity may become concentrated around configurations that closely resemble a smooth spacetime. When variations around that geometry remain small, matter can behave approximately as though it evolves on a classical background. A temporal parameter then appears within the approximation, allowing the ordinary Schrödinger description to return. This emergent time is reliable only while the gravitational state remains sufficiently classical. Decoherence may help maintain that appearance. A possible geometry interacts with matter radiation and inaccessible environmental degrees of freedom. These interactions suppress observable interference between widely different geometric alternatives. The surviving branches can behave as stable classical histories, each containing clocks, records, and causal sequences. Decoherence explains how classical behavior becomes robust, but it does not by itself select one interpretation of the total quantum state or settle why a particular history is experienced. Correlations provide another route. A subsystem that changes regularly can serve as an internal clock, while the rest of the system is described relative to its readings. Temporal evolution then appears through conditional relations rather than through motion against an external background. This idea can reproduce ordinary dynamics in suitable models. Its wider success depends on the quality of the clock, the interactions present, and the consistency of different clock choices. Thermodynamic conditions may explain why emergent time possesses a direction. The observable universe begins in an unusually low entropy state relative to its later possibilities. As correlations spread and entropy generally rises, physical records accumulate in one direction. Memories, fossils, radiation, and stored information align with that statistical arrow. Why the early universe has such low gravitational entropy remains an important unresolved question. Other approaches suggest that space-time and temporal order arise from quantum entanglement causal relations or deeper discrete structures. These proposals vary greatly. Some construct geometry from patterns of information. Others treat causal order as more fundamental than distance or duration. Some preserve a basic notion of sequence while removing continuous time. None has yet received decisive experimental support over competing descriptions. Observation remains difficult because expected quantum gravity effects usually occur at scales far beyond current experiments. Researchers search for indirect evidence in cosmology black holes, gravitational waves, high-energy particles, and precision measurements. So far, established observations remain consistent with general relativity and quantum field theory within their tested domains. No result demonstrates that time disappears fundamentally. The careful conclusion is therefore limited. Standard quantum mechanics uses time as an external parameter. General relativity makes temporal measurement part of dynamic geometry. Attempts to quantize that geometry can remove the external parameter and replace it with constraints, correlations, or approximate internal clocks. These developments show that fundamental time is not guaranteed, but they do not prove its absence. Time may be basic, emergent, relational, or expressed differently in a complete theory still unknown. Physics can describe why the question arises and identify the mathematical structures that make timeless formulations possible. At the present boundary of knowledge, measured change remains certain, while the ultimate status of time remains open. Across the observable universe, light carries records of change through expanding space. Clocks follow their paths through curved geometry, gathering different durations according to motion and gravity. Warm matter spreads energy, stars age, atoms oscillate, and physical records settle into the direction marked by increasing entropy. At every familiar scale, time remains measurable through change. Deeper within quantum theory, the description becomes quieter. A state evolves while time stands outside it as a parameter. Energy governs the pattern of that evolution, and atomic transitions provide stable cycles from which durations are constructed. Yet every real clock is itself made of quantum matter. Its readings carry uncertainty, its mechanism requires energy, and its state becomes correlated with the systems around it. When the clock is placed inside the description, change can be expressed through relations. One part of nature marks a sequence for another. When space-time geometry is also treated quantum mechanically, even the background that once supplied temporal order may lose its fixed form. A complete state can appear timeless while preserving internal correlations from which clocks, histories, and ordered records emerge. No experiment has established that time disappears at the quantum level. No accepted final theory yet determines whether it is fundamental, relational, approximate, or emergent. Physics instead reveals a boundary between what is measured securely and what remains unresolved. Duration is observed, clock rates are compared. Quantum systems change in predictable ways. The deepest explanation of that change remains open. The universe continues to hold its history in radiation, matter, geometry, and memory. Whether time exists beneath all those records or arises through their relationships is still unknown. At the present edge of understanding, the question rests without a final answer, while every clock continues its local and measured course.